Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on August 20th, 2025, about 5 days ago. The headline result is blunt. Functional benchmark wins do not guarantee safe or clean code, since models that pass tests still introduce bugs, vulnerabilities, and lots of code smells. The paper is titled, Assessing the Quality and Security of AI-Generated Code, a Quantitative Analysis. And as we will see later, the implications for deployment practices are quite significant. In short, across 4,442 Java tasks, every model produced defects, and static analysis flagged issues ranging from hard-coded credentials to path traversal risks. Alright, the reactions mix curiosity and caution. One prominent voice discusses diversifying LLM coding workflows, while others highlight that the study goes beyond benchmarks to analyze real security and quality issues. Engagement skews strong on the workflow thread with about 7,000 likes, while the research shares see modest interest. Moving from the social reactions, Table 1 presents the structural footprint of the generated Java code across the 5 models. The table shows that Claude Sonnet 4 emits the most code and complexity, which signals heavier maintenance costs, while OpenCoder 8b is the most concise with the lowest complexity. Comment density varies widely, with Claude 3.7 showing notably higher comments than GPT-4o. These contrasts matter because volume and complexity strongly influence review effort, refactoring needs, and long-term technical debt. Okay, the previous table compared structure and comments. Table 3 now summarizes defect metrics across the 5 models. Table 3 shows total SonarQube issues, lines of code, issues per 1,000 lines, and issues per passing task. Claude Sonnet 4 leads in total issues but also produces far more code, so its issue density is the lowest at 19.48. OpenCoder 8b is most concise, yet has the highest density at 32.45, while also posting the fewest issues per passing task at 1.45. The mismatch reinforces that passing tests do not ensure clean code. Alright, the previous table focused on structure and complexity. Table 2 now contrasts test pass rates with static analysis issues, so the quality signal becomes clearer. Table 2 shows that Claude Sonnet 4 leads on passing tests at 77.04%, yet it also averages 2.11 issues per passing task. OpenCoder 8b posts the lowest pass rate, but it has the fewest issues per successful task at 1.45. The mismatch indicates that passing tests alone does not guarantee clean or secure code. Okay, the earlier table highlighted overall defect densities. Table 4 now breaks those defects into types and shares. Table 4 shows that code smells dominate at roughly 90 to 93% for every model, while bugs sit near 5 to 8%, and security vulnerabilities hover around 2%. The consistent mix across architectures suggests a systemic generation pattern, not isolated quirks. That pattern matters because even small vulnerability percentages translate into many risky findings at scale. So the earlier table broke down bug severities. Table 8 now shows vulnerability severities across models, which matters most for security triage. The table reports that the majority of vulnerabilities are blocker or critical for every model, so high-risk issues dominate. Llama 3.290b shows the highest blocker share at about 70.73%, which signals severe exploit potential. GPT-4o and OpenCoder 8b also cluster near 2/3 high severity, indicating that automated code must undergo strict security scanning before use. So tying it together, 2 takeaways stand out. Passing more tests does not mean safer or cleaner code, and high-severity vulnerabilities remain common, so static analysis like SonarQube plus human review is essential. A code smell means maintainability issues, while path traversal means unsafe file access. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.